Welcome to Chemistry 101. We're doing chapter 6, actually the end of chapter 6, and 7 selected problems. Okay, so you need to be able to deal with energy in the form of heat energy that's within a covalent bond. So when you eat food, you're breaking these covalent bonds and they have potential energy that is turned into heat energy. So if you have energy of 526 cal, notice it's a lowercase cal. The conversion factor that you can find in chapter 6 is 4.184 joules equals 1 cal. I don't expect you to memorize these conversion factors. I would give them to you on an exam, but I do expect you to be able to convert. If you have to do calories with the little c to joules, then you would do cal on bottom, because that's not what you want, to joules on top. That's your question. And then you put 1 with cal and 4.184 with joules. You get your calculator out. 526 times 4.184. And we have three significant figures, 2200.784 joules. We'll put that in scientific notation. So 2.20 times 10, 1, 2, 3 joules. And that's three significant figures, and that is your answer. Convert energy of 145 kilojoules into calories. Well, we have joules to 1 calorie, so we're going to have to convert kilojoules into joules, and then that's not what we want, joules into cal. And so what's the conversion factor? You have to memorize 1,000 kilojoules equals 1 joule, because that's the metric. So 1,000, ooh, that is not right, folks. See, kilojoules is big, even though it has a little prefix. It is 1,000 joules into 1 kilojoules. So do not make that mistake. Catch yourself. Okay, so we have 1 kilojoules, 1,000 joules into the bigger unit, kilojoules, and then here we have 4.184 joules into 1 calorie. So 145 times 1,000 divided by 4.184. That is 34655.83 calories. And we want three significant figures, so we're going to put this in scientific notation. 3. Now we're going to round that 6 up to a 7 because that 5 would round that up. So 3.47 times 10, 1, 2, 3, 4, a positive 4 exponent. So that is the reportable number. Convert energy of 876 joules to units of calories. Now notice this is a big calorie. And so the conversion factor is there's 1,000 little cows for 1 big cow. So you would do joules to cow and then cow to cow. So 4.184 for 1, and then we have 1,000 little cows for 1 big cow. So 876 divided by 4.184 divided by 1,000, and that is 0.209 cal with a capital C. Okay, so you can see that in chapter 6. How much heat has to be added to 528 grams of copper at 22.3 degrees Celsius to raise the temperature of the copper to 49.8? So you can see a table of specific heats. Table 6.2. You do not have to memorize these. I will give you what you need. We're going to look for copper. And do we see copper? Yes, we see copper. Copper is 0.377 joules per grams degrees Celsius. Okay, so what does this mean? This is the amount of heat, 0.377 joules, that it requires to take 1 gram of copper metal to increase the temperature by 1 degree Celsius. And so all these substances have been measured about how much joule energy, heat energy, it takes to take 1 gram of substance and increase the temperature by 1 degree. What does this mean? Let's look at water. Water has a specific heat of 4.184 joules per gram degree Celsius. Now, do you think 4 is a lot bigger number than 0.3? Yes. Well, when you boil water and you put water into a copper in a pan and the copper's on the bottom, right? You got the copper on the bottom, the copper metal. What gets hot faster? What heats faster? The copper does. And so that metal gets heat really quickly. So it quickly can absorb heat, but then it also can cool down. Water has a very high specific heat, 4.184. So it takes a long time for it to absorb heat, but also it takes a long time for it to dissipate heat. That's why it's the solvent of life. But now you're going to need to use the equation that's in chapter 6, Q equals M times C times delta T. Sometimes you'll see me use C as specific heat S. Okay, so this is heat capacity. Sometimes you can use them pretty much interchangeably. You need to memorize this formula. You will use it for an open response and to work problems. So let's just go ahead and do delta T. Delta T is the change of temperature, and it's your final temperature minus your initial temperature. So delta T here, if you started at 22.3 degrees Celsius, that's your initial, and your final, the temperature of the copper is 49.8 degrees Celsius. That's your final. So you take 49.8 degrees Celsius minus 22.3 degrees Celsius. So 49.8 minus 22.3. And that is 27.5 degrees Celsius for delta T. Well, we have the heat capacity. We looked those up in the chapter. For joules, you want to do joules. What did we say that was? Oh, right here. So this is C, variable C. And the mass here, we've given 528 grams. You just want to make sure, this is important what I'm going to say, you want to make sure whatever you're using for your constant that you look up, you're using those same units. So here we got degrees C, so that matches. Here we got grams, and our answer then Q will be in joules. So always make sure your units cancel. Okay, so Q equals 528 grams times 0.377 joules, grams degrees Celsius, times 27.5 degrees Celsius. You have to have all your units if you want full credit on problems that I grade. 528 times 0.377 times 27.5. And that's 5474.04. Notice that the grams cancel out, degrees Celsius cancel out, and you're with joules. And so that is your answer. If you want it in 3 significant figures, you're going to have to take this to 5.47 times 10 to the 3rd joules to be perfectly correct. And you want 3 significant figures because all your measurements give you 3 figures. What is the heat change when 1.25 grams of water vapor at 185.3 degrees is collected to 102.1 degrees? So once again, Q equals MC delta T. Water, steam, vapor. I'm going to look and see. That's water, gas. They give you that. So we're going to use that for C. C equals 2.02 joules grams degrees Celsius. Mass equals 1.25 grams. And then our delta T is T final minus T initial. So if it's collected at 102.1 degrees, that's going to be your final, and your initial will be 185.3 degrees. And so 102.1 degrees minus 185.3 degrees Celsius is so it's collected at 102, so we're decreasing, so that's going to be negative 83.2 degrees Celsius. That's going to be important, that negative. Q equals 1.25 grams times 2.02 joules grams degrees Celsius times a negative 83.2 degrees Celsius. Just checking my math again. Okay, so 1.25 times 2.02 times negative 83.2. Q equals negative 210.08. And the units cancel out to be joules. What does that negative value mean? That negative means it's exothermic. That means heat is given off. So if you go from steam at 185 degrees and it's cooling off to 102, that heat is giving off to the environment. If it's positive, like this upper problem, then the copper is absorbing that heat. Okay, a mixture of carbon monoxide, hydrogen, and oxygen gases known as water gases can be used as an industrial fuel. So we're having an equation here. Is it balanced? 1 carbon, 3 oxygens, 2 hydrogen. Yes, it's balanced. The reaction releases 525 kilojoules of heat for every mole of carbon monoxide. So what you need to do is you need to make a conversion factor when you're given this. 525 kilojoules of heat equals, so this is for 1 mole of what? This is the carbon monoxide. And that would be important if you had different coefficients here. Okay, is this reaction endothermic or exothermic? So if it's releasing heat, so the heat is on the product side, it's releasing the heat, that would be exothermic. So if the heat is on the product side, then that's going to be exiting the reaction. That's exothermic. Okay? If the heat's on the reactant side and you have to put heat in and it's absorbing, so a word would be absorbing, that would be endothermic because you have to put heat into the system, the reaction. When I say system, it's the reaction. What is the energy change for this reaction in units of kilojoules per mole of carbon monoxide? Okay, well, in that case, it's just 525 kilojoules per 1 mole of carbon dioxide. When a 6-gram sample of coal is burned, it releases enough heat to raise the temperature of 210 grams of water from 24 degrees to 41.5 degrees. How much heat did the coal release as it burned? Okay, well in that case you're going to have to use Q equals ms delta T. Coal is carbon, and I must look up um, the specific heat of the carbon. So I'm going to the table. And we see carbon graphite. So we're going to go with carbon graphite. And like I said, I would give you these 0.708 joules per gram degree Celsius. So the mass is 6.00 grams. C, well, I say S, but your book uses C. So don't be confused there. C, this is C. And then the delta T releases enough heat to raise the temperature of 210 grams of water. Um, well, the reason why I'm thinking this, okay, the mass, you don't need to use carbon here. So what's the water changing? So this is kind of tricky there. You need to use the mass of the water. So to raise the temperature of the mass of the water is 210 grams of water. The temperature change of the water, so the delta T, the T of the final minus T of the initial is the water. So 41.5 degrees Celsius minus 24.0 degrees Celsius. And because we're using the mass of the water and the change of temperature of the water, we have to use the specific heat of the water. And so that is 4.184 joules gram degree Celsius. So now we'll do Q equals 210 grams of water times 4.184 joules gram degree Celsius times the delta T, which is 41.5 minus 24. So that's 17.5 degrees Celsius. So we have 2010 times 4.184 times 17.5. And so Q equals 147,172.2. And as you can see, that's joules. And so they're just saying a 6-gram sample of coal, when it burns, it releases how much heat. That's how much heat it releases. Now, calculate the heat of combustion of coal in units of kilojoules per gram. Well, this is joules, so 147,172.2 joules. We need to convert that to kilojoules. So joules to kilojoules, what is that? That's 1,000 joules equals 1 kilojoule. So then you say 1,000 joules for 1 kilojoule. So I'm going to take that number and divide by 1,000. Now I have 147.17 kilojoules, and then we want divided by the grams of coal. So this is where we now want to include our grams of coal, because we want kilojoules per gram. So we want that to be 1 gram. So we're going to take that number divided by 6, and so the answer is 24.5 kilojoules per gram. So that's how much heat is given off. This is what the coal burning plants do. They actually heat the water and make the water turn to steam. The steam will actually move the pistons, and that movement from the expansion of the gas to move the system is how you get like steam engines. All right, now this is where chapter 7 begins, and we're going to talk about electromagnetic radiation. So what's interesting, if you turn your focus to figure 7.6, you'll see the electromagnetic spectrum. I'll just call that the EM spectrum. And So what you'll see is you have gamma rays. So you got gamma rays, and then you have X-rays. You all have all been familiar with probably an X-ray before, where you have to put that metal shield to protect yourself from the X-rays because it's harmful. Then you have UV rays, ultraviolet rays, ultraviolet. What does ultraviolet mean? It means beyond violet. And you all know that that's high energy rays, right? These are high energy. That means high energy is harmful. So you probably put sunscreen on to protect your skin from the UV. That's beyond violet. So then you have visible. Okay, and you have Roy G. Biv. Okay, you see how I wrote it backwards? Because ultraviolet is right here with the violet. So you have like the violet, indigo blue, and then here you got the red, kind of the orange and the yellow. And so these are lower energy. So these are lower energy visible rays. And then you have infrared. So IR, which is what we see for like outer space and stuff, that is infra after red. You see, so that's after red, infrared. And then we have microwaves. So there was a time when people worried about standing in front of the microwaves when they're fixing their food. But as you can see, microwaves are less energetic and less harmful than visible. And then after that, you have radio waves. And we listen to radio waves all the time, right? On the radio. So this is high energy. So this is high energy on this side. I'm sorry, low energy. This is low energy. That means they're not harmful. That means they have longer wavelengths. So they have these real long wavelengths. Okay, and a wavelength is from that top to that top, that amplitude to amplitude. That's a wavelength, and you're going to see that written like that. Now these are high energy, X-ray, gamma rays. These are really bad for you. And so they have really short wavelengths. Okay? So they have really short wavelengths. I think I can do better than that for a wave. So maybe not. Okay, anyway, that wavelength is really short wavelengths, high energy. Okay, so what does it say? List 3 types of electromagnetic radiation that have longer wavelengths than visible light. So we are looking at, here's the visible, so infrared, microwave, and radio. You can write that down. Infrared, a microwave, and radio. What is the photon energy of light with a wavelength of 465 nanometers? So nanometers is how we measure the length, the wavelength, and that's this kind of lambda, called a lambda. And then energy, which we've been talking about energy in joules, equals h nu. Okay, so I say h nu. So nu is the V, this cursive V, and that is nu, and that is frequency. And frequency is directly related to energy. So I told you that these rays here have high energies. Well, that also means that they have high frequencies. And frequencies are when you stand at one point in time and you count how many times a wavelength passes through. And so you can imagine if your eyeball is here and you're counting over the 1 second and how many waves cross through, you're going to have a lot more for these shorter wavelengths than these long wavelengths. And what, because this formula, which you have to have memorized, is the energy is directly related to the wavelength or the frequency. Now the good news is this H is called Planck's constant, and you have it on your periodic table. So if you look at your periodic table, you'll see H equals 6.6261 times 10 to the negative 34 joules times second. So let's talk about the frequency. Frequency is how many waves cross at 1 second. So the units are 1 over s, and s is a second. Or you might see s to the negative 1, which just means 1, which is the same thing as 1 over s. All right, now the other formula you need is C equals lambda nu. So if you take a wavelength times its frequency, it's always going to equal the speed of light. C is the speed of light. And the good news is you don't have to memorize that either because that's on your periodic table. You can see C equals 2.9979 times 10 to the 8th meters. And you see second negative 1, which is the same thing as meters divided by second. Now, we are given, in this equation, we're given a wavelength of 465 nanometers. So that is lambda. So we're given lambda. And it wants energy. It wants photon energy. It wants E. The question wants E. So we have to go from the wavelength to the frequency, nu, and then we can put in the formula to get the energy. So we're going to have to use two equations. Now, also note that your constant, you always want whatever the constant is to tell you what units you want. C is your constant. You get your constants off of the periodic table. Your units for wavelength is meter, but you're given nanometer. So we're going to have to convert nanometer to meter. Then we're going to solve for nu, and then we're going to solve for E. And that's how you're going to approach this problem. Okay, so let's do just that. So to go from .465 nanometer, you put nanometer on bottom and you go to meter. Well, you know that there are 9 zeros in nanometer for 1 meter. So we're going to take 465 divided by 1, and then we count 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this gives me 0.123456465 meter. I'm going to count 1, 2, 3, 4, 5, 6 zeros, 465 meters. Okay, so now I have meters. So I've done that. Now I can put it in this equation and solve for nu. So I have C equals lambda nu. I have to isolate the variable nu. So how is it connected to lambda? Multiplication. So I'm going to have to divide both sides by lambda, the wavelength, to get those to cancel out. And then now I have C divided by lambda equals nu. So now I can take my constant, 2.9979 times 10 to the positive 8th meters over second divided by the wavelength in meters, 0.1234560 zeros, 465 meters equals nu. And the meters are going to cancel out, and that's going to leave me with s to the negative 1 or 1 over s. So now I'm going to put 2.9979 second E to the 8th divide by 0.000000465. And so now I'm going to get, the answer is nu equals 6.447 times 10 to the 14 s to the negative 1. And now I can put that in this equation where I have E equals Planck's constant here, 6.6261 times 10 to the negative 34 joules times second. Multiply that by 6.447 times 10 to the 14th reciprocal seconds. And you see how the seconds are going to cancel out. We're going to be left with joules, which is good because that's what you want for energy. So you take this times 6.6261 second E to the negative 34. And so your answer becomes 4.27 times 10 to the negative 19 joules. And that's how much energy of, and that's photon. You could say 1 photon or 1 mole of photons, depending on what you might read. How do you identify valence electrons from the periodic table? Okay, well, hopefully by now you've been doing this for your compound naming. Well, some of it. Okay, so when you look at the periodic table, group 1A has 1 valence electron. So like lithium has 1. Sodium has 1. And that's an electron. Potassium has 1. So all group 1 have 1 electron. Now, it will give that 1 electron up. And when that lithium gives the 1 electron up and becomes just plain lithium, that's where it gets a +1 charge. So when sodium gives up that 1 electron, it's a +1, and potassium is a +1. So let's look at how many protons are in lithium. Well, it's number 3. And so a plain lithium right here without a charge would have 3 protons and 3 electrons. The number of protons equals electrons. But when it becomes a +1 charge, the electrons become 2. And it has 1 more proton than electron because it gave up this electron. And that electron that it gives up is called the valence electron. So everything in group 1 likes a +1 charge, and that's because they have 1 valence electron. If you go to group 2A, you'll see that you have beryllium, which has 2 valence electrons. Magnesium has 2. Calcium has 2. And so when these elements form ions, metals always give up their electrons. This will form a 2+ charge. Group 2 plus 2+ charge. Well, let's look at calcium. How many protons does calcium have? Calcium has 20. So when it's neutral, it has 20 electrons. But if it gives up 2, then it has 18 electrons. And so the valence electrons are the electrons that are available for bonding. And one of the first steps of figuring out the bonding structures that you're going to be doing for the rest of the semester is counting valence electrons. So group 2A has 2 electrons. Don't worry about the transition metals. You can go on to the main group, which is group 3A, and you'll see boron and aluminum. And they typically are group 3, so they have 3 valence electrons, and that's why they form a +3 charge, and aluminum does a +3 charge. Carbon is 4A, and it has 4, And if it does form a plus charge, it would be a +4. Most of the time you'll see that it shares those electrons. Now nitrogen forms a -3 charge. So there's a thing called the Octet Rule. And the elements that definitely always obey the Octet Rule are your group 2. So well, not your group, it's called period 2. So row 2. So row 2 always has to abide by the Octet Rule. So for boron, there's always exceptions. Octet, well, what's an octopus? How many arms? 8. An octagon, 8. So an 8 is a complete shell, okay? A complete shell of outer electrons makes for happy molecules, meaning stable, low energy. So nitrogen is in group what? 5A. So nitrogen has 5 valence electrons. Now, I told you that nitrogen likes to form a 3-. So what it does is it will take, so it has its 5, and when it's in bonding, it will take another 3. 1, 2, 3. And what is that total? That totals up to 8. And so the metals, these plus charges, they'll just give up those electrons. It's so much easier just to give up an electron than to take. But now we're at nitrogen. We're at 5A. It's so much easier to take 3 than to give up 5. Okay, what about oxygen? You know oxygen's a 2-, and it's in group 6A. So if it's in 6A, then it has 6 valence electrons. So 1, 2, 3, 4, 5, 6, and it forms a 2- charge, so it will gain 2 electrons in bonding. And then fluorine is group 7A, so you're right, 7 valence electrons that it'll contribute to bonding. And then it forms a -1 by gaining an electron. So that's how you identify valence electrons, by the group number in the periodic table. Rank the following elements in order of increasing ionization energy. Well, what is ionization energy? By the way, in your book, you're not going to do electron configurations. So that means in Chapter 7, you're going to do the atomic spectra, electromagnetic spectra, some of the problems we just did. Now I'm skipping over all the electron configurations. We're not going to do that. That's quantum, so we're skipping over that. But the valence electrons are going to be important. You have to count those to add them up. Now we're going to go straight to the trends. So you are responsible for the trends in Chapter 7 of the periodic table. So you do have a table of ionization energies in Table 7.1. You do not have to memorize those, but you need to take a look at them when you're working your homework and see that those lower energy numbers, so the lower numbers, are the lower ionization energies. Let's just write that as IE. So that means to ionize. How much energy is required to remove an electron? To remove an electron. Well, notice that, let's just look at the first one. Lithium has an ionization energy of 520, and neon has an ionization of 2080. Well, neon has, what group is it? 8. So it's group 8. It has a complete octet. It does not want to give up an electron. Lithium, you know lithium forms a +1 charge. So therefore you should know that it's going to have a very low energy, ionization energy, because it always does this. Metals have lower, so write this down, metals are going to have lower ionization energies than nonmetals. Because if you give up an electron, you become a positive charge. So if you look here, look at oxygen. Oxygen 1314. Well, lithium's 520, beryllium is 899. So there you go. So ionization is the energy to remove an electron for 1 mole of substance in the gas phase. Can I answer that? Oh, we got to look at these three here. Okay, so do we have phosphorus ionization energy? Let's look at where they are in the periodic table. Phosphorus, oxygen, and sulfur. Increasing ionization energy. For these, oxygen is 1314. We don't have sulfur and we don't have phosphorus. I think these are ionization energy. Okay, so let's look at table 7.26. 7.26. Ionization energy, just so you know, usually increases going up a group and to the right. So you can see increasing ionization energy trend. So let's look at that. So, wait, I'm going to take that back. Let's look at 726. Okay. Give me some working space here. The reason why I'm having a little bit of trouble, ionization energy is easy to explain if you do electron configurations, but you all are not doing electron configurations, so I'm trying to figure out how to explain this without knowing anything about electron configurations. Okay, so I want you to look at table 7.26 and I want you to memorize the trend. So if you look at going down a group, so we're doing increasing ionization energy and it's the first one. So I need you to know that's ionization energy means the energy to remove the electron. As you can see, the lower numbers in group 1 increase going down a group. So you see cesium has a 376 ionization energy, where lithium has a 520. So going down a group is going to have a higher. So if you had to go down a group. And then if you go over, but what about going over? So let's look at lithium. Lithium is 520. Fluorine is 1681. So it increases, so it increases going up and over. So this is increasing ionization energy is up and over. So your lowest ionization energies are going to be, this is going to be your lowest, and this will be your higher, and then this will be the highest. And so these are the ones that have the highest are the ones that do not want to form a positive charge. So we have sulfur here. Sulfur is 999. Oxygen is 1314. Well, is sulfur below oxygen? Yes. So, and then phosphorus is 1012. So in this case, the increasing ionization energy is the highest is oxygen, and then the next highest would be phosphorus, and then the next highest would be sulfur. So at this point, I would want you to be able to look those numbers up. Rank the elements in order of increasing atomic size. The good thing about atomic size is you don't need to know anything about electron configuration. So you just need to know, these are the atomic size, so these are not charged. because it's different when they're charged. So this means the number of protons equal the number of electrons. So these are the atoms, the elements on the periodic table. You can see these nice pictures in your textbook, but they increase going down a group, and they increase going from right to left in a row. So between fluorine, you can see fluorine is really small, and lithium is bigger. Okay, so lithium is bigger, and then if you go all the way down to francium, it gets even bigger. And so that one of the ways you can think about going down a group gets bigger, well, how many protons does lithium have? 3. So it has 3 electrons. How many protons does francium have? 87. Well, it also has 87 electrons. So those electrons take up more space, and that makes it bigger. There's another principle why the rows are different. So now, looking at this, you have phosphorus is going to be the biggest, and then it's going to be sulfur, and then it's going to be oxygen. So, phosphorus and sulfur are in the third period, and the third period are going to be bigger than the second period. And then phosphorus is to the left of sulfur. So you do need to memorize that trend and be able to apply it. Okay, for each pair, identify the larger atom or ion. Well, magnesium has how many protons? It has 12, and so it has 12 electrons. Magnesium 2+ has 12 protons, and it has 10 electrons. And so what happens is it shrinks. So magnesium, and I can look at magnesium, they're saying it's 160, it's probably in angstroms, PM, so they're using PM. And then when you take away those 2 electrons, what it does is all the other electrons still feel these 12 positives in the center, and it shrinks. So it shrinks once those 2 electrons. So this, when you lose those 2 electrons, it's going to shrink. So the larger atom. So the larger, let's circle the larger or highlight it. The larger will obviously be magnesium. And that's when you have a cation, because cations will shrink because you're taking those electrons away. Phosphorus. Okay, so well, like if you look at the size of phosphorus, it's 110 ppm. Okay, now it has, let's look. It has 15 protons and 15 electrons. But then when you do P3-, well, it still has 15 protons, but now it has 18 electrons. And so if you take electrons away and it shrinks, what do you think happens when you add electrons? Yeah, it gets very big. So it's going to expand. So when you add electrons, this actually expands. And so the larger atom, or ion in this case, would be the P3-. And I think you can see that when you see the ions and the sizes compared to their atoms in Chapter 7. Okay, that wraps up the selected problems for 6 and 7.